Welcome to Complexity Made Simple. My name is Paul Allen, and today we're going to do a software tutorial, and we're going to look at the software of choice for design of experiments called DOE Pro. Hope you enjoy it.
Okay, in this tutorial we're back using Sigma Zone DOE Pro, and in this tutorial what we're going to do is take a look at analysing a full factorial. So the DOE that I have up on the screen here is a 4-factor experiment. So it's 2-level, a 2 to the 4 full factorial, and therefore you can see down here, look, 16 setups of the process. Just to explain what the process is supposed to be doing, the theory is that we are controlling the water level in a nuclear reactor, and we have 4 factors: plug pressure, bellow pressure, ball valve pressure and water temperature, and we are measuring water level. Now, in the same way that I mentioned with analysing a screening DOE, first thing we just ought to do is just take a little look at the yellow fields, take a look at our data set, ask a very simple question. Has my process been somewhere? Did I move it around? Let's have a look. Well, we got some 500s and some 400s early on. Then it moves into 800s and 600s, gets up to 900 here, back down 400s and 800s, moving around up to 1200. So look, I've really pushed the process around. The process has been to lots of different levels, and what that means usually is that when I do the analysis, something important is going to come out of this, because you've moved the process around. You've pulled 4 levers, and the 4 levers have had a dramatic effect on the result. So let's go do some analysis. So here we go, Sigma Zone. Now this is a straight full factorial, so I haven't done any screening beforehand, so I don't really know how this process performs. So when I go into Analyze Design, I'm going to stick with my original analysis, and I'm going to go to the marginal means plot, both y hat and s hat. Okay, up comes the S marginal means. Now, the first thing I'm going to do here is look for the biggest signal, and then I'm going to set it to minimize standard deviation. So in this case, here we have the big signal on the end, plug pressure, and the best place for plug pressure is down at 20. And that's a decision now that I'm going to write down. I'm going to go for that. Let me just check what effect that has on hitting the target. You can see, look, plug pressure is not having such a large effect. We've got 3 nice big signals here, so I can still hit the target perfectly well with plug pressure fixed to 20. And that's the way I always make a standard deviation decision. I'm always making a standard deviation decision from a graph, and that's my decision. I'm going to stick with plug pressure at the bottom end. I am minimizing standard deviation. Plug pressure is going to 20. Now, I made that decision. What I'm going to do now is I'm going to generate the model. So let's have a look. Sigma Zone, Analyze Design, Multiple Response Regression. Click Go. Okay, up comes the regression tables. Now, just a reminder for you, if you've used this software before, over here on the left hand side of the picture is the model to hit the mean, the model that moves the average around, known as the y hat model. Hat just means it's a predicted value, not an observed value. If I scroll over here a little bit, we have the S hat model. S is the standard deviation model. How are we affecting the consistency of the result? So on the left hand side we got y hat, on the left hand side we got s hat, and in the center here, this section here is all about being able to predict the result. Okay, so there's our first regression table. Before we go anywhere, I'm going to take a look at that R squared value down there. Look, so R squared 0.99, 99% of all the movement in the data was because we moved those 4 levers in the process. You have very little noise here. Everything is signal. Now I've got to be honest, this comes from a simulator that I use in class. 0.99 is very high on the R squared. That wouldn't be something that you would normally see in real life. And I've just got an example. Let me just go to a case study example of a real life model and the R squared. So here, look, this is an injection molding. Here's the model that they've got. The R squared, look, 0.77. That would be a little bit more like real life. The one next door to it, which is very high, cycle time. The reason why cycle time is very high, it has no variability. It's a computer controlled process. So if you set the machine up and you say it's going to be a 28-second cycle time, it always hits 28 seconds. Whereas the flatness, if you set the process up and you measure the flatness, every time the machine opens, the flatness of the parts are slightly different. Therefore, we get a little bit of noise. That degrades the R squared, and that's why we got 0.77. But that is still a very good R squared. The likelihood is we're going to be able to make the machine do what we want with such a good R squared value. Okay, let's go back. So let's go back to Excel, take a look. So the models come up now then. Because it's a full factorial, we have the possibility of analysing every term in the model. There are 4 main effects, A, B, C, D. There are 6 two-way interactions. There are 4 three-way interactions. And finally, there is a 4-way interaction. Now, some of these responses, some of these effects aren't true. You've taken a sample. As a reminder, you are never going to see 2 samples be identical, even if there is no effect when you are adjusting a particular setting. So we have to use the hypothesis test. It's here in the P2 tail column. Here are all the hypothesis tests. Now, as a reminder, the hypothesis test, low numbers are good, high numbers are bad, and it's going to go anywhere between 0 and right at the top would be 1. So for instance here, look, 0.94, this the ABD interaction, its p-value 0.94. A simple way to look at this is to just think, if I choose to leave that in the model, there's 94% chance I'm wrong. Well, if there's a 94% chance you're wrong, I think we ought to take it out of the model. And the way we take it out of the model, of course, is to delete the X. The others, these have got some big p-values as well. I'm going to take these out as well. What we're looking for is less than 0.1 or less than 0.05 on the p-value. So there's a 5% chance you're wrong. With this software, when you go below 0.05, the p-value goes red. If you go below 0.1, the p-value goes blue. So we're looking to regress this model down so that only red or blue p-values remain. So if I go, I've taken out the X's that I want to get rid of. If I regress again, okay, there it is. So if I regress again, let's just blow this up a little bit. There we go. So you can see the red p-values. I've got the AB interaction left. These p-values are not really going to change, so I'm gonna take these out now. So they're the last 3. Analyze, design, multiple response regression. Again, I'll just blow that up. And there we go. There's the model, all red p-values. That's exactly what we want to see. So that model is now ready to do some prediction. One last thing I'll just point out. The R squared has gone down slightly. That's always going to happen when you're taking terms out of a model. It always degrades the R squared ever so slightly. That is no reason to leave terms in the model. If the p-value is black, then that term must come out the model. We don't want to go leaving terms in just to keep our R squareds looking a little bit more healthy. So we've completed the y-hat model. Now let's scroll over here to the left hand side, to the right hand side of the page, and we've got the S-hat model. Now the S-hat model, look, doesn't have any p-values alive yet. There's a reason for that. It doesn't have enough data to calculate the p-values at this point. So you just turn it down a little bit, that's better. So we have to make a decision in a slightly different way. And the way we're going to make the decision is from the coefficient column, and we're going to go the opposite to the p-value now. Small values would normally stay in the p-value column, but when we're using the coefficient column, small coefficients can be removed. If you think about what the coefficient column is, the coefficient column is the equation. It is measured in whatever you were measuring. So in this case, we were measuring water level. This has probably got to be millimeters of water. So during the test, look, we hit an average standard deviation of 22 millimeters. We can happily throw things out of this model that make very little impact on 22 millimeters. So look, if I throw the four-way interaction away, if I'm wrong about that, I'll be wrong by 0.6 of a millimeter. It just is totally insignificant. So I can easily just take that out and not worry that I'm making a mistake or not. So regression. And now that I've done that, the p-values come alive. Now you can actually see that the p-values, there's only one blue p-value. So I'm just going to work this down fairly slowly. Let's see if we can make something. Let's see if we can make something happen. I'll take out the 0.25 and I'll take those out. I'll take the 0.6 out, and I'm going to regress it down. There we go. So you see, look, if you're patient with the p-value, sometimes they will come in. I'm going to remove the interactions there. Those are going to go. The three-way is going to go. I'm going to leave the main effect in for now, just to see what happens. Okay, that main effect clearly is not important. So those two are coming out. Okay, there we go, look. So what we've got, look, is just red or blue p-values. There's the S model. So the blue p-values, just a reminder, if they go below 0.1, it will go blue. If it goes below 0.5, so you can see that one there, look, for the plug pressure isn't quite below 0.5, so it stayed blue. But if it goes below 0.5, then the p-value goes red. And we just want to see red and blue p-values in the model. So now I've got a good S model, I've got a good Y-hat model, and the values in the yellow fields here are attached to those two models. And currently we are set at 35, 15, 150 and 85. And if we do that, we will land on a result of 700 millimeters with a standard deviation of 22.99. That's our current prediction. Now, what we would like this software to do for us now is to hit a target for us. The way we're going to do that is go graphs and optimization, multiple response optimizer. Now, if you remember, at the very start of this, we made a decision that plug pressure mustn't move from 20. So I'm going to take the design space as it is here, and I'm going to reduce the design space down for the computer. So I've put 20 in both boxes. So I'm stopping the computer from moving plug pressure. The reason we're doing this, we are in charge of standard deviation. So we've used the graph and we've taken charge of standard deviation. You are now going to put the computer in charge of hitting the mean. This isn't the way everyone tries to optimize, but it is the way that I prefer. I prefer to be in charge of standard deviation and let the computer have charge of the mean. You can let the computer take charge of both, but if you do that and the computer fails to hit the target, it tells you I can't get to the target. You're not always sure why. Whereas when you're in charge of one of the targets and it's in charge of the other one, it's a lot clearer to understand what's going on. So it's the way that I like to do it. Of course, you've also got these check marks for continuous values. So if some of these values only move in whole movements, whole points. So I'm going to assume that the bellow pressure can only go 10, 11, 12, 13. I've removed the check mark from the bellow pressure. And now the computer knows it won't give me fractional numbers. It will only give me whole numbers. And in fact, what I'm going to do, I'm going to take the check mark off all of them, because then it'll give me settings that make sense. Although in theory I could have a fractional water temperature, I can't control it like that. So I'm going to take the check mark away. I'm going to make it stick with whole numbers, and it will be a much more practical, optimized setting value that it gives me then. Click OK to that. Now I'm going to click through this window. This window, you would enable the CPK if you wish the computer to have control of the standard deviation as well, but we don't. So we're just going to click through it without doing anything to that window. And then what we have to do, we have to ask it to hit some target. So I'm going to ask it to go equals to, and I'm going to ask it to hit 725. We're going to go add constraint. Okay, so it's gone up here, and we've asked it to hit 725, and I'm going to hit optimize. Okay, now the computer's gone away. It's given itself 50 out of 50, and when it does that, what it's basically telling you is, yeah, I can hit 725. It's telling me down here, look, plug pressure 20, bellow pressure 20, ball valve pressure 170, and water temperature 70. Now, if for some reason you don't like that, you can press go, you can press optimize again, and it'll come up with a different set of values. Press optimize again, it'll come up with a different set of values. The computer is just a big calculator at this point. It's just trying to resolve the equation to 725, and it just has several different ways of doing it. If one of the choices it gives you is too expensive, you could always ask it to optimize again. If you have expensive regions, of course, that you don't want it to work within, you could have cut the design space down as we came into the optimizer. So I cut the design space down for the plug pressure, but you could have restricted the design space of some of the other variables as well. Not completely like I did when I made it go to 20, but you could have just made the computer work in a cheaper zone to see if that it could optimize with cheap settings. I'm going to accept these settings, and I'm going to press Settings to Worksheet. And now what it's done is it's populated the yellow fields with the settings for me, and it's now predicting, look, 24.993 with a standard deviation of 12. Now a key point, of course, with design of experiments is we now have to go back to the process. We are going to dial in these values, 20, 20, 170 and 70. We're going to run the process. We're going to take a new sample, and we're going to prove with a confirmation run that this knowledge is true. The p-values are an indication that they might be true. Everything might be true. The only way to confirm that the p-values are telling you the truth, because p-values can go wrong sometimes, the only way to confirm is to then do it for real. it's unlikely that you would make two mistakes back to back and that you would be lucky enough to land with those mistakes slap bang on the target that you're predicting there. If you dial those numbers into the machine and you get on average 724 millimeters of water level, this model is working perfectly well. Okay, so that's the way you do it. The p-values are telling you that there might be a true signal here, but the confirmation test is saying, yep, you know what, those p-values were telling you the truth. And that's the way to analyze a full factorial. You've created a prediction model. In fact, you've created two prediction models. The one over here, look, the y-hat model tells you how to hit the target. The one over here, the s-hat model, tells you how to minimize the standard deviation. And with those two models available to us, we can ask the optimizer to hit any target. And of course, it may say, I can't hit the target. The target is outside of the design space, and you have to decide what to do next. But that is the simple way that you analyze a full factorial, 2x4 full factorial using DOE Pro.
Well, I hope you found that useful. If you've got any questions about that topic, or indeed anything to do with Six Sigma or Lean for that matter, give me a call and I hope to hear from you soon.